Hello, welcome back. My name is again Michael Steele, and I'm one of the Math 3, Accelerated Math 3 teachers at Franklin High School this year, and I'm going to be working through problems from the Essential Skills Quiz model that gives you an opportunity to sort of see all the different varieties of questions that you could run into when taking that Essential Skills Quiz. As with the previous videos I've done, I think I've done 1, 2, and 10 at this point. I'm going to focus on going through each of the problems, like working them for you, of course, but also try to talk about the techniques and the ideas and sort of refresh you on not just here's how you do it, but here are the terms that are relevant, trying to get that vocabulary back into your mind, as well as, of course, notation and proper mathematical procedure as we proceed through. So this video is focused on solving equations, but these are all going to be quadratic equations, meaning that they are all degree 2, and they are going to be solved by factoring. So we're going to break each of these equations apart using one technique or another. I'm going to say there's like 3 or 4 techniques we're going to see in place, and then we're going to solve the equation. So it is key here, like sometimes I don't mention these things at the beginning, but it is key to mention that this is asking us to solve by factoring, not just factor, which means our answers are always going to be x values. They're going to be numbers. We're going to get a numeric value that makes each of these quadratic equations true. So without further ado, let's jump into these and start to get a feel for what this is going to look like, or what this might look like, because again, there's a pretty diverse collection of problems you could run into here. So our first question on Essential Skills Quiz topic number 3 is going to be this first 2-term polynomial, or this 2-term quadratic equation. So as the instructions say, they want us to factor to solve for x, and then we're supposed to write the factored form and then state the exact solutions. So basically our goal is to not just factor this, but actually state the solutions too. So we're sort of doing both of these pieces along the way. Obviously we're doing this to make sure you do both of them. Otherwise it's very easy to just kind of factor and be like, nah, I'm done. We want both of it at this point. So let's proceed here. So first of all, the interesting thing about this one is that we have only 2 terms. Also sort of interesting though, among those 2 terms, would be that the numbers themselves, 9 and 16 respectively, are both perfect squares. All of these things are leading us towards the technique that we're going to use here. And the technique that we're going to use in this case is called the difference of squares. So a difference of squares only is possible when you have 2 terms, and specifically when you have one quadratic term and one constant term. So we'll see in just a second a situation, an equation where there are 2 terms, but it's not set up for a difference of squares. So for us, what is difference of squares? Just as kind of that quick refresher. If we're going backwards here, like I'm not sure exactly what notation you were taught it in. I think this was the pattern that I was given. Basically that a squared minus b squared is equal to a plus b times a minus b. And if you're thinking to yourself, how the heck does that end up working? Well, just distribute this out. A times a is a squared. A times negative b is minus ab. Positive b times a is going to be positive ab. And then b times negative b is going to be minus b squared. And if you'll notice in the center, the ab terms are going to zero out. And we're left with a squared minus b squared. So in this case, sort of a backwards way to go through. I think that in reality, what we're looking at here, sort of what you want to keep in the back of your mind, as my computer refuses to help me actually copy that over. What you want to think of is sort of this technique. Again, there are other ways to get here, but this is a pretty standard one to approach with. So basically, this is what we're going to be using right there. In fact, let's change the color so we can look at it. We're going to be using that particular technique. So we want to break this apart. The difference is here we're going to start on the left side, and then we're going to produce the right side. So let's take a look at this. So first we have 9x squared minus 16 equals 0. So our goal is to break this apart. So what we should expect is, based on this, especially since there's no greatest common factor in there, 9x squared and 16 don't share any common factors, although we'll look at that a little bit more closely in a second. This should, if it fits our pattern, break up into 2 separate binomials, 2 separate linear factors. Based on what we have, we know that since this fits the form of a difference of squares, one will be plus, one will be minus. And then from here we want to look at the 9x squared and 16 and think, well, what do you multiply by itself to get 9x squared? And what do you multiply by itself to get 16? I think both of those are pretty clear. I could also point out that some people I've seen think of this as like, what's the square root of 9x squared? What's the square root of 16? The first one doesn't quite work the way you think it does, but the second one does, obviously. That's 4, and the other one leads you towards 3x. So with that said, this is going to factor into 3x plus 4, and 3x minus 4. So now for our answer, we were supposed to produce, it said, a factored form before anything else. And we've actually done enough to produce that factored form. Our factored form here is 3x plus 4 times 3x minus 4. And if you reverse the order there and did 3x minus 4 times 3x plus 4, totally fine. It's called commutativity. That's totally perfect. So there's our factored form. We've broken this apart. But remember, our ultimate goal here is to end up with solutions. We want to know what are the x values that make this equation true. Well, in truth, what we're going to use is called the zero products property. It's not necessarily something you have to know by name, but it's nice to know why. What that means is that if you have two things here, say these two things, and they multiply to 0, then either one or both of them must be equal to 0. And what that means is we can find our solutions by setting each of those two factors equal to 0. Now again, if you're looking at this going, why is he taking so long? I could do that in my head. Yeah, I know, but the point here is to refresh you in case you can't. So if you're watching this thinking, oh, I know all this, then maybe go look at a different problem. Just a thought. Here, though, if you're not sure, we're going to solve each of these equations. And again, you can move through them faster. Like I'm taking a pretty careful approach through here. On one, we're going to get 3x minus or equals negative 4. On the other, we'd add 4 to both sides. We'll get 3x equals 4. And then in both these cases, we'll divide by 3. So we're going to end up with, it looks like, and I'll go ahead and make our 1s here. I should have made 1s and made 0s before, my mistake. This is going to give us two values, x equals negative 4/3 and x equals 4/3. And that's actually what I'm going to go ahead and write up over here. So negative 4/3 and x is equal to 4/3. And our complete solution is what you see right here. Also, by the way, not something that you've necessarily addressed up to this point, but basically this is a degree 2 equation. Notice the highest exponent is 2. We end up with two solutions. That's part of what's called the fundamental theorem of algebra, something we'll see in the future, pretty near future, but the future all the same. But for the moment, it's at least worth pointing out to you. So there is our first one. This was, again, using a specific factoring technique. In this case, that technique was the difference of squares. Our second problem we're going to hit, question 3b, looks, I'd say superficially, just from a quick glance, looks a little bit like the first problem, right? It has two terms, it's quadratic, it hits all the big pieces. The difference here, though, is that we don't have something that easily breaks apart in the same way the last one did. I'm not sure if you recognize that, but notice here, we actually have an x in that second term. If we flip back to the first one, it was just 16 in that second one. So that was one thing. Second, although that 16 there might make you think of like perfect squares, that 2, in the front is not a perfect square. Now, it doesn't necessarily disqualify us, that 2 at least doesn't necessarily disqualify us from doing a difference of squares, but that x really does. So the technique we're going to use in this particular case is actually going to be the greatest common factor technique. And of course, when you hear the greatest common factor, you probably think of it by its acronym name. Like you and I both know it, I just feel like I need to write it out at least one time. That is the GCF. So we're going to use a GCF technique, which just means before we do anything else, before we attempt to factor anything else, we're going to check to see if there's any common factors between the first and second terms, or possibly even the first, second, and third terms, depending on what our equation actually looks like. So in this case, what I want to do is I want to look at 2x and 16x, like specifically those two. Now again, I think that for many of you, you can probably just look at this and recognize what the GCF would be, but let's play it safe. Let's say you're not 100% sure what that GCF is. Again, the purpose of these videos is more than just kind of let me do the problems for you. So what I'm going to do is I'm going to list out all of the prime factors, or break these pieces down to the smallest possible parts that I can. For instance, 2x squared, I'm going to write as 2 times x times x. For 16x, I know 16 is 4 times 4, which means it's going to be the same thing as 4, which is 2 times 2, times 4, which again is 2 times 2, and then times x. So for us, what we want to do is we want to find all the factors, like the biggest thing that can be contained is contained in each of those two terms. So what I notice right off the bat is the presence of a 2 and a 2. Likewise, I notice the presence of an x and an x. Now, outside of that, we only have an x left on top, And there's 3 2's left on the bottom. They have nothing left in common, so the 2 things that we've circled in red are going to represent the GCF, the greatest common factor, the largest factor that both of them share. So how does that help us? Well, it's actually pretty huge. We can rewrite this then with the 2x pulled out in front, and then multiply it times something else. In this case, I know it's going to be a difference because of the minus sign. So the question is, though, what's left over? If we've pulled out 2x, what do we have left? Well, we can see that over here really fast. If we pull out a 2x, there's still an x left over. And likewise, if we pull out the 2x from the second piece, 16x, we're left with 2 times 2 times 2, which is 2 to the third, or 8. So in other words, that polynomial up top, that equation, 2x squared minus 16x, is the same thing as 2x times x minus 8. Now, it says if you stop for a second, go, wait, why were we doing that? What was the point of making that move? The answer was, again, to factor it out, to break it apart so that we can use and apply that zero products property. Basically, if 2x times the quantity x minus 8 equals 0, that leaves us with 2 possibilities. Either 2x equals 0 or x minus 8 equals 0. Those are the 2 possible ways in which that equation can equal 0. Well, the first one, pretty simple. If you divide both sides by 2, you get x equals 0. And on the other side, if you add 8 to both sides, it ain't too bad. You get x equals 8. And after doing that, we've now actually done everything here. The only thing we haven't done is write it down on the side. That's on me. So I'm going to go over there and do that. So first, for our factored form, we did that. That was 2x times x minus 8. There are other ways to write it, but this would be the cleanest, I'd say most standard. And then for our solutions, well, we did that too. Looks like we got 2. X equals 0, and x equals 8. And if you want to, you can go plug those back in and check to see if they come out to be true. In this case, you'll find that they do, but I'll leave that portion to you. So there's our second one. This is the GCF, or greatest common factor method. I do have to tell you, you should always check for a GCF first, just because it's something that might otherwise derail your work as you're working your way through a particular problem. Here we did it first. Made the problem smooth sailing. So there is GCF factoring. The third problem we're going to run into here, question 3C, is actually what many people call the easy diamond, but it depends on where you came from. I am fortunate. I was one of the first, I think, classes of students in Elk Grove Unified that was taught the diamond. So basically this is how I've factored my entire life. Since before y'all were wee little ones, I've been factoring with the diamond. But, having said that, not everyone has. So I'll try to give you some extra techniques here to show you where things are coming from and why they're working. But this is, most people would call this a diamond problem or an easy diamond problem, even though, it sort of trivializes the real struggle that is factoring for the first time. So we're going to use diamond factoring here. So the question is, well, what in the heck is diamond factoring doing? Well, it's trying to set up sort of I want to call it almost the mechanics, so that you can figure out where those numbers of those coefficients actually came from, and then you can effectively factor. So for us, what we're going to do is we're going to take first, like there's a 1 hidden in front here, we're going to take first the product of the leading coefficient and the constant. So that's going to be 1 times -5, which is -5. And then we're going to ask ourselves, what 2 numbers do you multiply to get -5, but add up to -4? And this has to do with sort of multiplying out 2 binomials. If you wanted to play with it, you could do something like x plus 1 times 2x minus 3, and just sort of see how things play along. But for us, we just have this sort of simple arithmetic puzzle here. We want to figure out what 2 numbers multiply to -5 and add up to -4. Well, I can see that pretty fast. I'm thinking 5 and 1 are going to combine effectively, because 5 times 1 is 5, but then 5 plus 1 doesn't equal 4. So instead, we need to think about where the negative signs might go. And I'm thinking, since we need them to add up to a negative, we'll go -5 and +1. So let's see if that's true. -5 times +1 is equal to -5, and -5 plus 1 is equal to -4. Chef's kiss. So we got it. Cool stuff. Now what do we do with it? Well, many of you already know that this immediately leads to us having x minus 5 times x plus 1 equals 0. In other words, we have factored out our polynomial right off the bat. So cool, we got it. Now, having said that, though, there are diamonds that aren't quite this quick, and that can be sort of a bad habit to get into, especially if you've had trouble factoring in the past. So it might be worth pointing out that what we're really doing here is setting up something that we can factor through a different technique called factoring by grouping. So what I'm going to do here is I'm going to use this box strategy. So again, we got a diamond in a box. It's like a wedding or marriage proposal of some kind here. So what do we got? I'm going to break up all these terms here, because what we really did was we wrote negative 4x instead as x squared minus 5x plus 1x minus 5. So what I'm going to do is I'm going to rewrite this in here with exactly that form. And now what I'm going to do is I'm going to pull out GCFs in each direction. We're going to basically see if we can't transform and figure out where this equation came from. So from here on the first row, I noticed that both x squared and 5x have an x in them. So I'm going to pull out an x. If you're wondering about the signs, I always pull out the closest sign. So whatever's on the outside, I'll pull. So there was no sign there, so I just kept it x. And the next line, we have positive 1x and negative 5. The only thing we can pull out is plus 1. Now the eagle-eyed among you might already notice, hey, wait a second, didn't we have x plus 1 a second ago? We did. Likewise, going upwards, like x squared and 1x both share an x, and there's no sign up here, so we'll keep it that way. And then minus 5x and minus 5 definitely provide us a lovely little minus 5. What we just found were the two factors. So basically there is some extra stuff happening in here. In a sense, it's like we're breaking something apart in such a way that GCFs work out really nicely. I don't think you have to think about that while you're doing this particular problem, but it's nice to be reminded that it comes from somewhere, especially because we're going to use this technique if we get to a hard diamond problem, which I'm sure we will in a second. But for us, that was sort of the key. Now we have our equation equal to 0. We can either have x minus 5 equals 0, or we can have x plus 1 equals 0. Each one requires a single step of algebra to sort of resolve itself. One we're adding 5, the other we're subtracting 1. On the left, we get x equals 5. On the right, we get x equals negative 1. And there are our solutions. X equals negative 1 and x equals 5. And if you're staring at that going, well, why did he rewrite them in a different order? That's just kind of an old habit. I was trained on sort of always writing the smaller value first, so I did it that way. But there we go. So we got to see an easy diamond. Again, easy is just the relative term. It's a little bit simpler. There's a fewer steps. If you want to take some shortcuts here, you can. But basically, there is the diamond method. Break it apart so we can factor out some GCFs. Contrast that with this one. This is what we'd call the hard diamond. And you might have noticed in the last one, if you did watch it, which hopefully you did, in this so-called easy diamond, I never really explained what made it easy. Like, why is this an easy diamond versus something else? And in reality, the thing that made it easy was the presence of a leading coefficient of 1. So back here, we just had x squared. It's the same thing as 1 times x squared. Here, though, we've got a 4. So though the diamond is definitely still something that we're going to be able to take advantage of, we no longer have the convenience of that 1 in front. That can only be broken down as 1 and 1. Instead, we've got this 4. So let's see what that's going to look like. So just as before, we're going to begin with doing the diamond. We just have to take into account that 4 that's there in front. So in here, I'll set up my little diamond. This time, as we did before, we need to multiply the first coefficient times the constant. So that's going to be 4 times negative 2. 4 times negative 2 is negative 8. And then once again, our middle coefficient is positive 7. So we're looking for, this time, two numbers that multiply to negative 8, but add up to 7. And I feel pretty confident, once again, that we're going to be able to get that pretty fast as 8 and 1. Now, of course, which one goes where? Well, we need the sum to be positive, so the bigger number has to be positive. We'll have positive 8 and negative 1, which you can do a quick little mental check to make sure it actually works. It does. So with that said, we have our pieces. Now here, though, we don't have that shortcut option. We can't just go x plus 8 and x minus 2. There is a technique that sort of pushes in that direction, and you can do some stuff to get there. In fact, one of those techniques is called the butts up method, that a student I tutored back in the late 2000s actually did. But for us here, basically let's use that box technique. Let's break this apart. So what I'm going to do is I'm going to first think of this as 4x squared plus 8x minus 1x minus 2. So that's what we want to break apart. Of course, it's equal to 0, but that's sort of beside our point. So I'm going to draw out our little box here. Again, there's lots of techniques. You could also use a split the middle technique. Maybe I'll show that if there's time at the end. We're going to put one of these pieces into each of the spots, starting from left to right and then up to down. So 4x plus 8x minus 1x minus 2. And if you're not sure how I do the next few steps when I pull off these little GCFs, I'd encourage you to go back to the first problem, or sorry, the third problem in here, 3C, and listen to me describe that in a little more detail. So for us, looking side by side, 4x squared and 8x share a 4 and an x. Minus 1x minus 2 is just a minus 1. Again, we're taking the nearest sign, which negative would be. Going upwards, they both have x's, and the nearest sign is nothing because we have 4x squared. And then finally, plus 8x and minus 2. That's going to just give us a GCF of plus 2. So basically, we have our value here for our factors that break up and that make up and comprise 4x squared plus 7x minus 2. So in other words, we now have factored it. 4x minus 1 times x plus 2. And this whole thing is equal to 0. So good news for us, we got that. We can put the factored form down here on our answer sheet. For the solutions, we do have to do a little bit more work. Again, we'll apply the zero product property. That means 4x minus 1 is going to equal 0, and x plus 2 is going to equal 0. I'm going to go ahead and I'll do some of the work on this side. So if we add 1 to both sides, we'll get 4x equals 1. And then we'll divide both sides by 4. And we're going to end up with one of our solutions, whereas over here we'll subtract 2 from both sides, get x equals negative 2. So based on all of that little bit of work, we get that x is equal to negative 2. Again, I like to go negatives first, or smaller number first. And then finally, x equals 1/4. And other than writing this into our little solutions area, we've gotten this taken care of. We got it. Well, we got it. Do I have the box drawn correctly? No, but now we got it. So there is 3D. Again, we're using the diamond, but this time it is what we call the hard diamond because of that non-1 leading coefficient. But we handled it basically the same way. Finally, our last one here. And this is one that I'm going to tell you right now. I plan to use a different technique than maybe you'd be taught in a different class. So this one looks just like, to me, the previous one. Looks super similar to 4x squared, plus 7x minus 2. You can sort of see the superficial similarities. The difference here, though, is that there is a possibility of doing something a little bit different, specifically because we have 4x squared and 25, which are both perfect squares. In other words, you can write something times itself to get those two things, and those some things turn out pretty nice. But having said that, when I see this, all I can think to myself of is the diamond itself. And I think that it's a lot, I don't know if better is the right word, but I think it's preferable to have a flexible technique down really well than to focus on sort of smaller, other less frequently occurring techniques, and then sort of dilute your whole understanding. So I'm going to approach this with a more general technique. What I'm going to do here is just what we did on the previous page. I'm going to use the so-called hard diamond. And if you're thinking it wasn't that hard, good. Although I will admit that there's something kind of fun about calling it a hard diamond, because diamonds are notoriously hard, according to science, or geology. So there you go. The more you know. Dun, dun, dun. Okay, let's diamond this thing up. So first we're going to take the leading coefficient and multiply it times the constant. That's going to be 100. And then positive 20. So we are looking for two numbers that multiply to 100, but add up to positive 20. And I'll tell you right now, I know lots of facts for 100. 1 by 100, 2 by 50, 3 by 33 and a third. Okay, it's not quite a fact. 4 by 25. Oh, yeah, there's one. 5 times 20. 10 times 10. Oh, look at that. 10 times 10. I think we have a winner. 10 and 10, both of them positive, by the way, will give us our 100, because 10 times 10 is 100. And 10 plus 10 is going to give us 20. Well, I think we did what we were supposed to this time. I'm proud. So let's go see what happens from here. So what did we just do? We broke up the middle term. In fact, some older mathematicians or textbooks might refer to this as splitting the middle. That's literally what we're doing with the diamond. So there is our polynomial. We're going to box it. We're going to pull a Manny Pacquiao and box it. And then run it for governor, I think. Was it governor or president? I can't remember. not kept up on Manny Pacquiao's Wikipedia page lately. So from here, what do we got? Well, let's fill in all the individual pieces. 4x squared plus 10x plus 10x plus 25. And now let's pull out the GCFs. So plus 5, 2x. Oh, that's kind of the same. 2x again. And oh, that's also the same as the first one. Plus 5. So what it turns out is this thing factors into 2x plus 5 times 2x plus 5. And of course, all equal to 0. So in other words, we get the same factor twice. So when it comes time to actually write this in factored form, we could totally write this out. We could also instead just write it as 2x plus 5 squared. In other words, square it because there's two of them being multiplied together. So I'm going to write it that way. I think it's the cleanest way. It also appears on the key that Ms. Nakamura gave me, so good sign. And as far as the solving, this is sort of a 2-for-1 deal. Once you solve one, the other one comes for free. In both cases, we get 2x plus 5 equals 0. In fact, I'm a Pokemon fan. I'm going to write ditto right here. It's the same thing. So moving some stuff around, we'll get 2x equals negative 5. And we'll divide both sides by 2. And we're going to get that x is equal to negative 2.5, also known as negative 5 halves. From there, to get credit, we just need to record our solution. So let's do it. Ooh, that's one of my better boxes, freehand. I'll take it. But having said that, we've now done this technique totally correctly. We used the hard diamond again, and we were able to work our way through. If you're curious, I'm not going to go through this particular one because I don't think it's necessary to learn this other technique. You could also have treated this one as a perfect square trinomial. There are some indications that it's going to turn out to be a perfect square, but I am being 100% truthful when I say that I don't actually look for perfect square trinomials at all, simply because they don't occur very often. And when they do, like in this case, I can just kind of do the problem using the diamond. So I don't bother. And again, you be you. If you find a better way or a path you feel more comfortable with, hey, you are empowered to do that. But that's just not the technique I'm going to approach. I'm trying to be realistic about how many techniques you know. And hey, this cuts out one less technique for you to focus on when you're trying to kind of pull together all of your factoring knowledge. So with that said, that was the final problem on question number 3. So that's going to allow me some time to go take a short nap while this video renders. So as with all of them, I hope this was helpful and informative and useful to you. If it wasn't, that's okay too. Thanks for watching in any case. And with that said, I hope you have a great rest of your day. Thank you, and see you again soon.